All right, welcome everyone. So today the topic is going to be more discussions on depth first search. So we'll talk about an algorithm for computing the strongly connected components of a directed graph. And we'll also talk about computing articulation points in a graph. Another very compelling example of the power of depth first search. So let's begin by reviewing some of the definitions of strongly connected components. And then we can discuss an algorithm for it. Okay. So this is what we discussed in the end of last lecture. So just reviewing that. So consider a directed graph. Now note that when you have a directed graph, the notion of connectivity is more complicated. Because say you have two vertices u and v, you may have a path that goes from u to v. You may have a path that goes from v to u, or you may even have situations where you have something that looks like this. So technically what one has down here is not a path that goes from u to v, but it is a path if you were to make all the edges undirected. So you have these sort of different situations, and so to define connectivity, is not trivial. So we introduce a notion called strongly connected. So u is strongly connected to v if there is a path from v to u and a path from from u to v and a path from v to u, which means you can go from u to v and you can go from v to u. So you can think of that as a cycle that connects u and v. So when u and v are strongly connected, there is a cycle that goes through u and v, right? Because you can start from u, follow the path to v, and then come back to u. So I'm going to denote that by this sort of squiggly arrow. So u arrow v means u as a path to v. And v arrow u means that v as a path to u. So I put a double arrow saying u is strongly connected to v. Now this squiggly arrow is an equivalence relationship. So what does that mean? It satisfies the three properties of an equivalence relationship. It means that first you have something called symmetry. If u is strongly connected to v, then v is strongly connected to u. And this should be apparent just by looking at the definition or by looking at this picture, right? The roles of u and v are completely symmetric here. It is reflexive, meaning that u is strongly connected to u. So this in some sense is a trivial, it's just true because a single vertex is a path. So path is about reachability. So you can always reach from u to itself. And importantly, you have a notion of transitivity, which means that if u is strongly connected to v and v is strongly connected to w, then u is strongly connected to w. And again, you can see that by maybe drawing a picture. So suppose v is strongly connected to w. Now observe that u also has a path to w, and w has a path to u. Both of them, those paths go via v. So that means that u is also strongly connected to w. So this is an equivalence relationship on the set of vertices. Now, there's a fact about equivalence relationships is when you have an equivalence relationship on a set, then the set can be partitioned into equivalence classes. So equivalence classes are maximal subsets so that all pairs of vertices are strongly connected to each other. So written over here, an SCC, a strongly connected component, is a maximal set of vertices such that for all u and v in the set, u is strongly connected to v. Think of this as the analog of a connected component in the undirected sense. In the undirected sense, you have connected components. In the directed sense, you have strongly connected components. And pictorially, you think of it as you have a set here, which is a strongly connected component, and a set here, which is a strongly connected component. So suppose this edge does not exist. And you have edges that go from one strongly connected component to another. And so you'd like to find these strongly connected components. So again, as I discussed last time, you can think of an application of this as if you're looking at the Twitter follow graph. You're looking at who follows whom. You might imagine that celebrities form like a strongly connected component amongst themselves, and other people of different interest groups follow strongly connected components. So strongly connected components is some way of trying to find out which are groups of people where there's communication sort of happening in cycles. Whereas communication that goes from, let's say, celebrities to followers is one way mostly. Right? So this is one way, this is one kind of a simplistic application of strongly connected components. And in practice, what people do is more than strongly connected components, but you can think of this as the simplest version of this kind of a problem, where you're trying to find out in a directed graph, you're trying to maybe separate vertices into groups. Now, we discussed last time that given two distinct strongly connected components S1 and S2, there cannot be edges from S1 to S2 and from S2 to S1, because if there were, then S1 and S2 would merge to become a strongly connected component itself. Now, we defined a graph H on the strongly connected components. So there is a vertex in H for every strongly connected component. If there is an edge in G from S1 to S2, from the connect component S1 to S2, then there is also an edge S1 to S2 in H, a single edge. This is the graph on strongly connected components, and this graph is a DAG. Okay, so the problem that we wish to study is given G, find all strongly connected components. More generally, construct the DAG on strongly connected components. So I will talk about the first problem, and I will give you a beautiful linear time algorithm to compute all strongly connected components. This algorithm uses depth first search. So at this point, let me pause and take any questions you have about this, because it's important that you understand what has been discussed thus far, because the rest of the lecture is going to be based on these concepts. Any questions? No? Okay. Hang on a second. Let me just... there. So let me actually give you the algorithm. And you'll see, I mean, it is sort of remarkable, and it's very elegant algorithm to compute strongly connected components. So the algorithm to compute strongly connected components. So first step is run DFS on G to get the finish times. So I will denote this as the finish time, right? Now, what we'll say is compute G reverse obtained by reversing every edge of G. So what that means is, if you have UV in G, then in G reverse, you have this edge. So this is G, and this is G reverse. So G reverse basically just flips the direction of every edge. So you can go ahead and compute this. You can either, make a separate data structure, or you can do it within. One can implement this different ways. Now here is the clever bit. You run DFS of the reverse graph, processing vertices in decreasing order of the finish times. Remember, these finish times were obtained in step 1. Right? The finish times. So you run the depth first search. You run a depth first search on the reverse of the graph, processing vertices in the decreasing order of the finish times. And then finally, every tree output by the DFS of step 3 is a strongly connected component. and that's it. The running time is O of m plus n. So just to be clear, because step 1 runs in O of m plus n, step 2 also runs in O of m plus n, because you're just reversing a graph. So you can just read through the graph and reverse. You can reverse the graph quite easily. Just read through the adjacency list and then build a new graph. And step 1 and 3 also, because 3 is also just a DFS. And of course, 4 is just outputting things. So this entire algorithm runs in linear time, right? Step 1 is a DFS, step 3 is a DFS. So it boils down to running 2 DFSes, right? You're running 2 depth first search processes, and that gives all the strongly connected components. Any questions about the algorithm itself?
Yeah, I don't understand step 3.
So you're running depth first search on the reversed graph, but remember the depth first search has an order in which it, okay, so maybe let me show you what I mean by that. So depth first search has this has this for loop, right? This for loop is done in reverse order of finish times. This for loop, step 3. And one can do the same with this for loop as well. It's done in reverse order.
So does that just happen because...
I'm sorry, say that again? So whoever, the first person asking the question, go ahead, continue with your question, and then whoever interrupted can ask. Yes?
Does that just happen because the graph is reversed when you run the second DFS?
Or no, you have to do it. You have to do it explicitly, because if you think about this for loop is the order on the vertices, which has nothing to do with what the edges look like.
So do you have to sort the finish times?
You'd have to sort by finish times, but as we discussed before, you don't actually have to call a sort. And I will show this to you in just a second. So remember that you could just build a stack which has all of the vertices in reverse order. When we did topological sorting, we did this. Right? Every time a vertex finishes, you just push it onto a stack. And that way the stack will then contain all the vertices in reverse order of finish time. Let's sort of pull that up. We discussed this before. We said that you run depth first search on G. When any vertex finishes, you push V onto a stack. So this has a topological ordering. So that would be, which would be the reverse order of finish times if it was a topological order. But it's not a topological ordering at this point, but this stack, you can just, anytime a vertex finishes, you push it onto a stack. And the stack has the right ordering. Does that make sense?
Yeah.
Okay, so someone else had a question. Someone interrupted.
Oh, I was also worried about the running time, but I guess it's fine.
Yeah, right. So because, this, you use a stack. Use a stack, to get in O of n time. Okay.
Wait, so I guess one more question about processing vertices in decreasing order.
Mm-hmm.
Is that also like the first vertex that you choose has to be the vertex that was finished last? Or you're
Yes.
free to choose whichever vertex you like to start, but then every time you run the for loop, you have to.
No. It's every. You should think of it as essentially the stack over here is going to be what you use in step 3 of DFS.
Oh, I see.
Now that you have the stack, you just sort of process in that order.
Okay. You don't so within
the adjacency listed actually doesn't matter.
Okay.
Within the adjacency listed is we should check the proof. I as we prove this should be clear. I don't think it matters. I think the only thing that matters is this.
Okay. So when you're actually running DFS on a single node, you don't care how you build that tree.
You don't care about the ordering over there.
Okay.
Yeah, but we will verify that as I discuss the proof whether what I said was true. But okay. So this is the algorithm. So just two DFSs. Any questions? All right. So let's try to think about, okay, so let's just to give ourselves some understanding. And I think that once you see this, things should be clear. So let me first ask you a question. Suppose G is a DAG. What is the size of a strongly connected component of G? A, is it just 1? B, is it n? Or C could be anything. So let me launch the poll. What is a strongly connected component in a DAG? Okay, so there seems to be some confusion on this matter. It's just 1. It's always 1, because if you think of a DAG, for u not equal to v in a DAG, if u has a path to v, then v cannot have a path to u. Otherwise, it would form a cycle. Remember, we said a strongly connected component when you have a strongly connected, when U is strongly connected to V, there is a cycle that connects both U and V. But if G is a DAG, there are no directed cycles. And hence the only strongly connected component is the trivial one, which is the singleton. So every vertex is its own strongly connected component. Right? So what happens in a DAG is each vertex is its own strongly connected component. And so what we require in this algorithm is that we have to get all the vertices as singletons. So step 4 should output singletons. Is this clear? Any questions about that? Right? So this will really help you understand what's happening in this algorithm. Let's run this on a DAG. And we know that in a DAG, the output is very simple. Every vertex is its own component. Okay, now what I'm going to do is I'm going to pause. So read through this and see if you can argue that when G is a DAG, this is going to simply output singleton components. Okay, so I'm going to pause for a minute and want you to think about it, and then we can discuss. And think about what is the reverse order of finish times when you have a DAG. All right, does anyone want to make an argument or sort of guess as to why is it that when G is a DAG, each tree output is a singleton vertex?
So, if I may.
Yeah, go ahead.
The first DFS will basically the reverse order will be a reverse topological sort.
It's not reverse, but actually a forward topological ordering.
Pardon?
It's not a reverse topological ordering. It is a topological ordering. Remember the reverse order.
I see.
Go on.
The finish times. Okay. Yeah.
Yes.
It'll be topological ordering.
Yes.
And in any case, when we compute the reverse thing, step 2, there will be no. Basically, there should be no edges. So it'll be all just single vertices?
In this, no, because, so let me give you an example. So let's just say here's your DAG. Okay, here's the DAG. This is G. Well, G reverse looks like this. So let me give these vertices 1, 2, 3, and 4. Sorry, I'll make this bigger. So this is 1. This is what the reverse looks like.
Oh, I see. My bad.
Right? So the reverse has edges in it.
Mm-hmm.
The reverse definitely has edges in it.
Mm-hmm. Could you bring up the algorithm again?
Sure. And I would like to keep maybe this example in front of you. And I think this example might be useful. So you see that actually it's not that the reverse has no edges. The reverse will have edges in it.
But is it the case that the reverse will have no outgoing edges?
No, it does, right? Like, look at this.
So
this is the
when
graph.
you're processing it in reverse order of, in decreasing order of finish time.
So, you are right.
Yeah. So for example, in the left graph, 1 will sort of be on the top of the stack.
Okay.
Right?
Yes.
So when you pop 1,
yes,
you can see that there's nothing going outwards.
Yes.
And so, there is nothing to go from there. So you'll have to process the next element on the stack.
No, but okay, good. But let's slow down a bit. So you're right that there is nothing. What this means is that the DFS tree is just going to be a singleton one.
Yeah, exactly. Yeah. So DFS ends for 1. Yeah.
Yes. Okay, good. Then what happens?
And here we'll simply remove or mark 1 as visited.
Okay, good.
And therefore it'll not be in our next DFS graphs DFS trees that we create. And now the next one that we will do is either 2 or 3.
Okay, so maybe 2.
Maybe 2. And in reverse, it doesn't have any outgoing edge to a vertex that's not visited.
Right.
Therefore, it'll be a singleton in its tree.
Right. So then good.
And the rest is just a
so on and so forth.
Induction on this, yes.
Yep. So because this is a topological ordering, 1, 2, 3, and 4 is a topological ordering. Sorry, I should have drawn this better. So that's 2. So 1, 2, 3, 4 is a topological ordering. And if you see what happens here, when you run DFS, processing vertices in this order, 1 will become its own thing, singleton, then 2 will become its own singleton, then 3, and then 4. Now, observe how important it is to process vertices in the topological ordering. If you processed vertices, suppose we process in order 2, 1, 3, 4. Then it will break down because it would start from 2 and then it would output 2, 1 as a DFS tree. And of course, 2, 1 is not a strongly connected component. So what is key is that this is a topological ordering. Now you can also observe that instead of 1, 2, 3, 4, if it was 1, 3, 2, 4, the same thing would work. Any topological ordering is valid. Just for this example. Does this make sense? Any questions?
Is it really required to create sort of that G reversed? Could we not have said that if we just get a topological ordering from G and then process vertices just based on the topological ordering, or is that the same thing?
Say that again.
So we run DFS on G, we get some topological ordering,
right? And
then I'm trying to see why is it required to reverse the graph.
Okay, so because let's say that you did DFS in this ordering. If you started from 1, then you would actually visit everything and you would just pull out the whole thing as one DFS tree. Remember, the strongly connected components of these are all singletons.
Got it, yeah.
You have to reverse so that you can get these things as singletons. Does that make sense?
Yes, yeah.
Instead of reversing the graph, could we just run DFS on the opposite of the topological order?
It's a good question.
G?
It's a good question. So
yeah.
in this case, you can. And if you think about it, just for pulling out individual vertices, it would work. Because if this is the topological ordering, you know that if you start a DFS from 4, you cannot visit any other vertex. So 4 will come out, then 3 will come out, so on and so forth. Now, the question that we need to understand is, now you'll see that, hold this question, because now we want to do strongly connected components. And we need to see whether that idea will work. That idea will fail for strongly connected components.
No, this is the strongly connected component, right? But on a
for
DAG.
This graph, but I mean, in general, we want strongly connected components not for a DAG, but for a larger graph. Okay? Any questions about that? Okay.
I'm not sure that's clear to me. Could you repeat it?
So I'm just saying that right now, what you said was correct for this graph. And in this case, I was only looking at finding strongly connected components of a DAG. But we need to consider what's going to happen when we want to find strongly connected components in a general directed graph, and whether this idea works where you where you do things in the reverse or topological ordering. So anyway, hold that thought. So my point is, hopefully you understand this example. Let's visit another example to get some more intuition. Now suppose instead of the graph being 4 vertices, each of these was actually a strongly connected component. So maybe what 1 is really it's some kind of graph inside which is all strongly connected. Right? So I'm just going to refer to this as S1, S2, S3, and S4. Okay, and now there could be multiple edges that go from here to here. You know, there could be some edges that go from there to there, edges that go from there to there. Multiple edges going between these. Within, this is like a strongly connected component. Okay, within these, this is a strongly connected component. I hope this picture makes sense. Right? Each of these, S1, S2, S3, and S4, is a strongly connected component. And so within each of these, there are cycles, otherwise this is a DAG. Okay, now let's try to understand what happens in the algorithm. And so, okay, so this is G. Now what's going to happen in the topological ordering? So we don't have a topological ordering, right? We don't have a topological ordering. We just get a bunch of finish times. Is there something that you can argue about the finish times? Is there something that you can argue about the finish times?
The reverse is topological ordering.
So there is no such thing as a topological ordering in this graph because the vertices, there are cycles. There are cycles amongst the vertices.
Certainly, you have to finish some vertex in S3 after S4, after some vertex in S4. Like, I guess it's that there's some vertex in S3 that finishes after a vertex in S4, and there's some vertex in S1 that finishes after a vertex in S3.
Why?
Because either you got to all of S4 some other way, like maybe you started in S4 and got everybody in S4, or you got into, like, there was an unvisited vertex in S4 that had a parent in S3.
Mm-hmm.
And then when you've processed the parent, it would finish after.
Mm-hmm. So what you're observing is, as soon as you visit a vertex in a strongly connected component, you will end up visiting all the vertices in it. Right? This is essentially the white path theorem, right? It says, look at the first vertex. So look at S4. And at some point in this process, you're going to visit some vertex in here. Now, as soon as you visit this, you will visit all the vertices in here because there is a cycle, like essentially you can get from this vertex to every other vertex. So let's just say, I'm just going to call this U4. If you look at the DFS tree, you have U4, and then all of S4 are going to be descendants of U4. Now, furthermore, from this, there are no further descendants because there is nowhere else to go. You cannot have S2 being a descendant because then that would mean that there is a path from U4 to S2, which we know is not true. So this entire strongly connected component is essentially a descendant of U4. Now let's look at, let's say, some vertex in U3. So what's going to happen is, let's look at this vertex here. There's some vertex that has an edge, and I'm going to refer to this as U3. Now, if U3 is visited before U4, so U4 is somewhere in here, and U4 is somewhere. If U3 is visited before U4, then there is a path from U3 to all the vertices in here. So U3 then becomes an ancestor, in which case U3 will finish before U4 and all the vertices here. If not, if when U3 was visited, everything here was visited, well, then you know that U3 is going to finish later. So in all cases, essentially, there is a vertex in S3 that finishes after all vertices of S4. And the same thing kind of holds with that directed structure. That there is always a vertex in S1 that is going to finish after everybody else.
Is it? We can't guarantee that though, because S1 is connected to S4 though, right?
You can guarantee that, because if you look at, so I claim that this is always going to be true. You can guarantee that there is a vertex in S1 that finishes after all the vertices in S4.
Oh, I meant the claim that S3 will finish after S4.
You can claim, yes, you can say that. S3 will finish after S4.
Even if S1 is connected to S4?
So if S1, what could happen is maybe S1 visits all of S4, right? The DFS visits all of that. But then that's fine. When U3 gets visited, if everything here is already visited, then obviously U3 is then starting after S4 finishes. So it's going to finish after S4 finishes.
Oh, I see.
If it starts after, then it's going to finish after. Your problem is, what if it starts earlier?
Right.
But if it starts earlier, there is a path, right? So essentially, you look at this one vertex that has a path. Does that
So
make
can
sense?
we, is there like any, like, so kind of what I'm thinking is, if there's like, the ones with the longest path will always end last.
It's not the longest path. It's really about, if you look at the DAG of the strongly connected components, that's giving you the information. Because the strongly connected components themselves form a DAG.
Right.
When you look at that DAG, the DAG structure tells you who's going to finish last. Or rather, you get some kind of, I will generalize this, but essentially, hopefully you're starting to see the idea that there is no such thing as a topological ordering of the vertices, but there is such a thing as a topological ordering of the components themselves. Although we don't know what the components are. What we know, if you think about this, is the very last vertex to finish. The very last vertex to finish is going to be in S1. The last vertex to finish is in S1.
That's because we're starting from S1, right?
No, even if you didn't start from S1, no matter where you start, the last vertex to finish is in S1. I want you to process that statement. Like, I'm saying this again, right? It doesn't matter where you start. The last vertex to finish is in S1. Take this argument again, right? You know that there is a vertex in S1 that has an edge to S2. this vertex has to finish after S2. There is a vertex in here that has an edge to S3. This vertex finishes after S3. So vertex in here, it finishes after S4. So there is a vertex that finishes after every single component. Hence, if you look at the one that maximizes, it's in S1. The last vertex to finish is in S1.
Will all of the vertices in S1 finish after all the other vertices in the graph?
Will all the, okay, that's a good question. So it's not all the vertices. It's that there exists some vertex.
And we can apply this argument to any of the components, right?
Say that again.
We can apply this argument of why S1 will always finish last to any of the components to get a general idea of the ordering.
Exactly, right? But of course, the problem is when you look at just this reverse ordering, it could all be like mixed up with each other, right? So it's not obvious how this is going to play out.
So will it always be the case that any component without any outgoing edges will always finish last?
So say that again?
Any component, for example, S4, without any outgoing connections will always finish last?
No, the other way around. It's S1 that finishes last.
Finish first.
Finish first. Let's start with the opposite, right?
Okay.
The component that doesn't have incoming edges,
right,
is will finish last.
Right.
Well, I mean, the thing is, okay, so even that is not entirely true. So let's be a little bit more careful about that, because there could be two components, S1 and I'll call S1 prime. Between these, you don't know who's going to finish.
I see.
Last.
Okay.
Right? So you only have one. All you know is that if you look at the component that finishes last, it does not have any incoming edges.
Okay, I see.
That's what you know.
And the same argument can be applied when we were talking about the ones with the most incoming edges. Like, we can't guarantee that'll finish first.
Okay, one has to be a little careful here because it... Sorry, say that again. You mean which will finish first?
Right. So let's say we had like another, like an S4 prime that had 3 incoming edges. We can't guarantee which one will finish first.
Yes, you can't. Yeah. You cannot guarantee. But but let's be a little careful. So it's not. Let's make sure that. Okay. So what we know is that. Right. So okay. So let me draw another. So suppose you had some component that looked like this. I'm just going to call this S5. Right. There's some edge that's coming out from here. You also don't know anything about the relative order between S2 and S5. It could happen that S2 finishes before S5 because S2 might start a DFS, visit all of S4, come back and finish. So S2 and S4 might finish and then S5 would finish. So S5 could finish after S2 even though S5 doesn't have any edges going out and S2 does have edges going out.
Oh, okay, I see.
It only works one way.
Right.
And that's why you have to be careful about doing this thing with the reverse topological ordering, as someone had suggested earlier. Right? So you have to be careful about the reverse topological ordering. And okay, but I will come back to that in a moment. So now you see that S1 is going to finish last. So if you took the reverse, there's S1, S2, S4, S3, S5, and we had kind of edges going this way. I'm sorry. I have to reverse everything. Now note that when you start at S1, you're going to visit all of S1, and that is going to come out as a strongly connected component. Because we know that the very last vertex to finish is in S1. Now, if you remove all the vertices in S1, the very last vertex to finish, other than those in S1, is going to be in either S2 or S3, and then you can repeat this argument. So it's similar to the DAG argument. Right? And maybe, one had this S1 prime as well. So is this clear? Any questions about this? So hopefully you're seeing the idea of why this works.
Just to be clear, everything in S2 will finish after S1, right? Like every vertex in S2.
No, that is not true. Because you could suppose you started in S2. Okay?
Yeah.
And maybe that DFS is going to go visit everything in S4, come back, and then finish.
I'm talking about the graph on the right-hand side.
On the right-hand side.
After it's reverse.
So repeat what you said.
So every vertex in S2 should finish before S1. I mean, after S1.
Will finish after S1. Indeed, it's actually even going to start after S1.
Right.
Forget finishing. It's going to start after S1.
All right. Yeah, makes sense.
Because you have set up the ordering so that you are going to start in S1. You're going to start in S1 because you're doing it in the reverse order of finish times in G. And the reverse order of finish times in G ensures that the first vertex that finishes is going to be in S1. Hence, S1 gets visited before anything else gets visited.
Right. Got it.
What is important to note is that if you look at the strongly connected components in G and the strongly connected components in gref, they're the same. The SCCs are the same. Right? It's just that the ordering between the SCCs is reversed. But the ordering is the same. Therefore, when you pull out the components in G reverse, you get the strongly connected components of G. You see, what's remarkable about this algorithm is that, it's just using the finish times. It's just using the finish times. Okay, so far so good. Any questions about this? Okay, so now I'm going to sort of try to formalize this argument. Let me formalize the argument. So the first claim that I'm going to make is consider SCCs S1 and S2 in G such that there is an edge from a vertex in S1 to S2, right? So this is a strongly connected component, and there's some edge that goes between this. And what you know is within here, you have some sort of, everything is connected through a cycle or whatever, right? This is a strongly connected component. There's S1, there's S2, and you have this edge. Okay? Then I'm going to write something. I should have defined this earlier, but I'll say the finish time of S1 is greater than or equal to the finish time of S2, where the finish time of any set of vertices is simply the max over all vertices in the set of the finish time of that vertex. So it says that the largest finish time in S1 is more than the largest finish time in S2. All right. So let me sort of sketch out the proof. Is this clear? Do you see that this captures the argument that we were discussing earlier? This is sort of capturing this argument here. Right? Remember, all it's saying is in terms of finish times. And it's just saying that the maximum finish time in one is more than the maximum finish time of the other. It doesn't say anything more than that. And the argument, as you might imagine, is exactly, what was discussed earlier, where you're considering something like considering this vertex U3, considering the vertex U3 and what it's connected to, so on and so forth. So let me write this down more formally. So I'll say consider the edge. I'll call it U1, U2, where U1 is in S1 and U2 is in S2. Right? Okay. And so let us break up into two cases. Let's break up into two cases. So I'll say case 1 is the discovery time of U1 is less than the discovery time of U2. So here's the discovery times, here's the discovery of U1, and this is the discovery of U2 at some point. So when U1 is discovered, U2 is unvisited.
Could you move the paper?
Oh, I'm sorry. U2 is unvisited. Right, so consider the situation. But I just realized that here's a better way of doing it. So I'm going to introduce yet another notation. Sorry for this. Let V2 be the earliest discovered vertex in S2. V2 be the earliest discovered vertex in S2. And so we'll come back to this case, but okay, so what are the properties of V2 that we can prove? What do we know about V2?
It's discovered before any other vertex, or I guess that's truism, but
hence,
when
what is
you discover V2, you'll also discover the rest of S2.
Exactly.
V2's finish time is later than the finish time of every vertex in S2.
Right. V2's finish time is going to be more than the discovery time of every vertex in S2 because, so we know that, so when V2 is discovered, all vertices in S2 are unvisited. Since S2 is a strongly connected component, there is a path from V2 to all, I'll call it W in S2. Right? There's a path, so, or rather, this is badly written. I should say, let me rewrite this. I'll say, for all W in S2, there is a path from V2 to W. There is a path from V2 to W inside S2. You can actually argue that this entire path is also contained in S2, right? And I didn't explicitly prove that, but you can show that there is a path that is going to be contained in the strongly connected component. Because essentially sorry?
Can we say this is because of the unvisited path theorem?
So this statement over here I haven't talked about the unvisited path theorem yet, right? This is just saying that there is a path that's completely contained in here.
Okay.
Because essentially, if you look at the definition of strongly connected component, or if you look at the definition of strongly connected, you'll see that if there is a path from V2 to W, then all those vertices are also going to be in the strongly connected component because they can get to anywhere. They can get to W, and W can get back to V2, and V2 can get to all those vertices. Okay. Moreover, this path is unvisited. Now we say by the unvisited path theorem, right? All W in S2 are descendants of V2. And because they're descendants, hence V2 finishes latest in S2. Okay, so we'll come back to this in a moment. So we have this vertex V2, which is the earliest discovered vertex. And we know that V2 finishes the latest.
Is this to say that because there exists some edge from S1 to S2, and the edge in S2 completes before the one in S1, we can conclusively say that because V2 finishes first or last in all of S2, then V1 must finish after, S1 must finish after S2?
You have to be a little careful here, right? Because so V2 may not have a connection to U1. Remember, U1, U2 is the edge that we have. So U2 might be somewhere here.
But isn't if there's an edge connecting S1 to S2?
Yes,
we can say U2 will always be the earliest discovered in S2, and then by the same.
No, that is not necessarily true, because maybe there is some other stuff that's going to discover these vertices. Maybe there is something else out here, and then you start a DFS from there, and that's going to discover all of this.
Oh, I see.
You see? You don't know what's going to happen here, so you have to do a case analysis. You have to do a case analysis here. Any questions about this? So V2 finishes the latest because it's the earliest discovered vertex in U2. In S2, I'm sorry. Okay, so now we need to sort of so now we know that this max is really the max in S2 is achieved by V2. And indeed, this statement is true for any strongly connected component. And now if you think about it, you should be able to make this argument. I'm just going to make another statement here. I'll say let V1 be the earliest discovered vertex in S1. V1 finishes latest in S1. So actually, what's going to make more sense is to do this case analysis with V1 and V2 rather than U1 and U2. So my apologies for this confusion. So look at the, I'm going to maybe draw this on a separate page. So here is S1, here is S2. And so you have this edge U1, U2. But the earliest discovered vertex is V1. These could be equal. V1 and U1 could be the same, V2 and U2 could be the same. But we're just saying that V1 is the earliest discovered vertex and V2 is the earliest discovered vertex. And what is convenient about the earliest discovered vertex in S1 and S2 is that the earliest discovered vertex in S2 is the one that finishes the latest. The earliest discovered vertex in S1 is the one that finishes the latest. So these are sort of the two important points that we have. So hopefully this helps you sort of understand what is happening in this. And now let's do the case analysis. I just want to make sure that I'm doing this carefully. So let me just talk through this and let's see if this is going to work. So let's just say that V1 was discovered before V2. So V1 is discovered before V2, and V2 is the earliest discovered vertex. Note that there is a path from U2 to V2, and there is a path from V1 to U1. So if V1 is discovered before V2, then there is a path from V1 to V2, all of unvisited vertices. Hence, V2 is going to be a descendant of V1. And indeed, all of S2 is going to be a descendant of V1, and therefore the finish time of V2 is later. On the other hand, if the discovery time of V1 was more than the discovery time of V2, so V2 was discovered earlier, then, okay, so this is where it's going to get interesting. So let me do this sort of step by step, and you'll see what's going on. So let me do my case analysis again. I'll say the discovery of V1 is less than the discovery of V2. The discovery of V1 is here. So when V1 is discovered, all other vertices in S1 union S2 are unvisited. Hence, there is a path of unvisited vertices from V1 to V2 as follows. V1 to U1. Why? This is because S1 is a strongly connected component. Then the edge U1, U2. And this is by assumption. Right? We assume that there is an edge going that way. And then finally, a path from U2 to V2, because S2 is a strongly connected component by the unvisited path theorem. V2 is a descendant of V1, hence the finish time of V1 is more than the finish time of V2, and this is exactly equal to the finish time of V1 is equal to the finish time of S2, right? Because V2 is the maximizer. So that takes care of this case. So case 2 is where it gets interesting. Suppose the discovery of V1 was more than the discovery of V2. This is the discovery of V2, and this is the discovery of V1. And let me put my parentheses here. Okay, and let's draw this again. S1, S2, U1, U2, V1, V2. So V2 is discovered first. So now, can you complete the proof?
Yeah.
Okay.
Because V2 starts is the first discovered in S2, and it must also be the last finished in S2.
Correct.
And then because there's no edges, if there's no edges connecting S2 to S1, S2 is complete. So then V1 is discovered after the finish time of S.
Almost,
but after the completion of S2.
But maybe there are some edges that go from here, and then that leads to something else, and that could then connect back to S1.
But then wouldn't that be strongly connected, and they would all be one component?
Good, right. So this is the thing you need to assert, exactly, right? So what you're saying is if V1 actually got discovered in the process of V2, then the entire thing becomes a strongly connected component. Exactly. So one needs to basically make that formal. So your argument is completely correct. And so now let's just make this formal.
Can we use the unvisited path theorem again? By saying,
how?
well, so I'm saying we have like an if and only if statement about something being a descendant of something else, and then we have like some inequalities, right? And I'm saying like, well, we know that V1 isn't a descendant of V2 because there's no path. So that's not the unvisited path theorem. Sorry,
it's a parentheses theorem.
Yeah.
Exactly. No, that's exactly what I was going to do. With the parentheses theorem, this argument becomes very easy. You're right. You just use the parentheses theorem over here to argue that this must close before this opens. Right now, I'll just do it right now, right? So if the finish of V2 is less than the discovery of V1, then sort of obviously the finish of V2 is less than the finish of V1, and then the proof, we're done. Right? So V1 is finishing after V2. If the finish of V2 was more than the discovery of V1. So what does that mean? It means that this is finishing somewhere here. Then by the parentheses theorem, the finish of V1, so this has to finish in here to be a correct parenthetical statement, lies in the range discovery of V1, finish of V2. But then V1 is a descendant of V2. So that means that essentially there is a path that goes from V2 to V1. Yes, go on.
The second point isn't exactly like a proof by contradiction. What would you say this is? Just case?
No, this is going to be a proof by contradiction.
Oh, okay.
This part is going to be a contradiction.
Okay.
Yeah, the first, yeah. So if this is the case, but then V1 is a descendant of V2, V2 is a path to V1, and then S1 union S2 becomes a single SCC, and this is a contradiction. Sorry, I'm writing it out a little short because, I want to proceed with the lectures.
I'm sorry. So for the first one, where we assume that if finish of V2 is before discovery of V1, we would, in a formal proof, we would need to write some more stuff, right? Saying that.
Say it again. In which case? Which case?
In the first case, where
this
finish
one?
of V2, where finish of V2 is less than discovery of V1. So I just wanted to confirm that when we are formally proving this, we would need to establish some more things, right?
In this case, there is nothing more to establish, right? Because you know that the finish of V1 is greater than the discovery of V1.
Finish of
because every vertex obviously finishes after it's discovered.
Mm-hmm.
In this case, this is enough. I don't know. There is no step that's missing here. I'm just saying that this being less than the finish time, that's sort of obvious, right? Because the discovery is less than the finish.
Right.
So the finish of V2 is less than the finish of V1. Okay, I guess you just have to say that we argued that V2 finishes the latest.
Yeah.
Yeah, you need to say that V2 finishes the latest, but we already proved that, and therefore there is a vertex that finishes after all of S2, and then that's it. Therefore, V1 finishes after all of S2.
Sure. Okay.
So it's just one more sentence.
Mm-hmm. Okay.
Is that clear?
Yeah.
Okay, good. Okay, so does this make sense? So this is in some sense the key argument, right? That the finish of S1 is more than the finish of S2. Whenever there's an edge from S1 to S2. And now if you think about this, what you can argue is in the reverse. So now this is where we need to complete the argument. And I'm just going to write this out as a claim that again you consider SCCs S1 and S2 in G such that there is an edge from S1 to S2. Okay, in the DFS of G reverse, when the first vertex in S2 is discovered, when the first vertex in S2 is discovered, all of S1 has already been discovered. Okay? So what am I saying? So here's S1 and S2. I'm drawing the situation in G. So in G, there is an edge that goes from here to here. Now, when you reverse, so maybe I'll draw this over here in G reverse. You have S1 and S2. And there's an edge going in the opposite direction. when the first vertex in S2 is discovered, everything in S1 has already been discovered.
Is this assuming the ordering using the...
Exactly. This is assuming this ordering that you get from here and the fact that you order things. Exactly. Exactly.
Should there be some way to like state that in the claim?
I mean, okay, so what I meant was in the DFS of D reverse done in the algorithm. Sorry, I should have, what I meant was really this D reverse done, this DFS done. Right? And so essentially, this is like the key claim. There are multiple ways of doing this. I'm not going to sort of write out all the entire proofs because we don't have much time left. But let me just say that another way of proving this is that we can also prove what you can prove basically by induction. By induction over the topological ordering. So you can prove this by induction over the topological ordering. That I'm just going to write a statement that the first k components output by DFS of G reverse are all distinct strongly connected components. If you combine all of these, you should see what is going on. This is sort of the fundamental key. So you can argue that some vertex in S1 is finished before S2 in the first DFS. So in the second DFS, you will always process a vertex in S1 before you process S2. So you're going to visit all of S1 as soon as you process that vertex before you visit S2.
Professor?
Yes?
Couldn't we make this claim stronger then by saying all of S1 has finished?
You can say all of S1 has been finished, yes.
Oh.
Yes, you can. This would just be easier to prove, but you can also, yes, you can prove that all of it has actually finished. Yes. Okay, are there any questions about this? I'm going to make this into exercises and ask you to sort of finish the details. Questions? Okay, so just to poll you, just want to ask, has everyone followed this discussion? A is yes, B is, no. Okay, so it seems that most of you follow. So I'm going to end the discussion. Not that we have much time left, we have 15 minutes left. So I'm just going to tell you a little bit about articulation points, and then maybe I will convert much of that into exercises, because this is the last lecture that I want to have on depth-first search. So let me show you, let me just sort of reiterate that the main point of what we did so far is, is define strongly connected components by running two depth-first searches, right? So you can run two DFSes, and you can get all the strongly connected components. So I'll tell you about cut vertex, or what are called articulation points, just the cut vertices. So it's quite simple that a vertex V is a cut vertex, also called an articulation point. If the removal of V disconnects G. So I'm going to think of G as simple and undirected and connected. Okay, so you have some connected graph, and a vertex V is called a cut vertex if its removal disconnects the graph. So for example, if you have a graph that looks like this, we've got lots of vertices here and vertices here. There's some connections in here and some connections in here. If you remove this vertex, then there's no connection between these. This concept and generalizations of this concept have appeared a lot in social network analysis, because if you have such a vertex, sometimes these are called information brokers, meaning that they have connections to two different groups who don't have connections amongst themselves. So these vertices tend to be important. And often when you do social network analysis, you're trying to find who are the vertices who are actually taking information from one side and communicating with the other. Often, sometimes when they do analyses on researchers, they'll see some researchers who are present in two different communities, which are different from each, where there's no other connection. And these people are quite successful because they're able to take ideas from one and port it to the other, and vice versa. So this is called a cut vertex, right? And so a graph could have many cut vertices. So maybe you have another cut vertex here. For example, if you had a single edge going in from there, then this vertex would be a cut vertex, so on and so forth. Of course, if this connected back into this, then this vertex is not a cut vertex anymore, because there's a path that goes along. And so the problem is find all cut vertices in G. Okay. Can someone give a simple algorithm that runs in polynomial time? Just a simple algorithm that runs. How will you find all cut vertices?
Just cut every vertex and then run a search to find connected components.
Exactly. So you could delete a vertex, and then you find all connected components. And if there are two connected components, then you're done. You found a cut vertex. Put the vertex back in, then delete the next vertex, so on and so forth. Right? So what is the running time?
It's n times n plus m.
Right. It's n times n plus n, so it's quadratic time. Right? It's essentially mn plus n squared, which is quadratic. So the simple algorithm is simply for all vertices in G, so construct G, I'll say minus V, by removing vertex V from G. You could just run BFS or DFS on G minus V. if there is more than one connected component, which is the same as saying if there's more than one tree in the forest, then you output V. Right? Output V as a cut vertex. Okay, so these steps, these run in O of m plus n, but this is running n times, and so the running time is essentially O of mn plus n squared, and this is quadratic. Or depending on what m, but it's quadratic or worse. And so this is the simple algorithm. And it turns out, so sort of our good friend DFS is we can actually find all cut vertices by running a single DFS. Which is quite remarkable when you think about it. Now, obviously, in the next 5 minutes, I cannot show you the entire proof, or even the algorithm. But the basic idea is really it's not that difficult when you think about it. So let's kind of see what's going to happen if we have a cut vertex somewhere. So we have this graph, and here's our vertex, and here's the rest of the graph. Here's everything else. So think about, so DFS is going to have to start somewhere. So I'm just going to sort of simplify this picture. I'm going to refer to this as S1, S2, and this vertex as V. Okay. So let's say DFS starts in S1. Just say, suppose. Now observe that there's no way for DFS to visit S2 without visiting S1. To visit any vertex in S2, V must be visited first. So at some point, V is visited. Now, when V is visited, all of S2 is unvisited. So essentially, all vertices in S2 become descendants of V. Okay, so that's, you have V, and then you have S2. And what is important is there's no edge that comes out from here. So no edge can go out. It turns out what you can argue is that, so here is, the DFS tree. Remember that in the end, there's just going to be one DFS tree because the graph is connected. There cannot be any edge of this form. This is, if you recall, is called a back edge. So a back edge is an edge, is edge to an ancestor. What you can show is that there's a claim that, okay, so I'm fudging a few things, I'm leaving out a few details. So technically what I'm saying is incorrect, but it's almost correct, is there is no back edge from a descendant of V, so I should say strict descendant of V, to a strict ancestor of V. So there's if and only if V is a cut vertex. Now I'm fudging things because technically if the DFS actually started at V, then you have another special case. But if DFS did not start at V, it started somewhere else, then essentially what you know is that as soon as you come into V, you'll visit all of this and then backtrack and go out. There is no edge that takes you anywhere else. So there is no back edge that goes from S2 to an ancestor of V. And it turns out that you can prove that there is no back edge from a strict descendant of V to a strict ancestor if and only if V is a cut vertex. And furthermore, in linear time, you can sort of pick out all the vertices that satisfy this condition. It looks complicated, but once you break it down into a few basic steps, it's actually quite doable. And based on that, you can actually show that one can compute all the cut vertices by running a single DFS and then processing the tree. And this can be done in linear time.
What if V has more, like V has maybe some more descendants that are in S1, right?
V, yeah, so technically it's, okay, so there is no back edge from actually a strict descendant of a child of V. So that's why I said this is technically incorrect. So there's actually a child of V that satisfies this property. That child is the first child in S2 that is seen.
Ah, okay.
Okay. Yeah, good point. So the thing is, I didn't want to put that in before because then it becomes confusing. But essentially, there is a child of V that satisfies this property, which is indeed the first vertex in S2 that is seen. Okay. So you can, you know, this is a formal claim. I will write down the claim in the exercises and I'll provide it. And then you can basically, I'll put together a series of exercises using which you can show that all cut vertices can be found by running a single DFS. Okay, so I'm going to end the lecture here. This ends our discussion of depth first search and graph traversals. And when we start on Thursday, I will probably change the topic and maybe we'll do like dynamic programming or greedy algorithms. Okay, so I will end here and take any questions that you have.